All right, we're back. We're in Calculus 1, Chapter 3, Section 8 of Stewart's Calculus book, and we're looking at a couple of homework problems in WebAssign. In the previous video, we finished talking about, it was a long conversation, but we looked at a number of examples of problems. We talked about process, we talked about concept, we talked about some backstory, and that has allowed us to arrive here at a couple of problems that I want to look at from a homework assignment. And in problem number 2, which is where I want to start, we have a population of protozoa which develops with a constant relative growth rate of 0.8329, which I've already labeled as our K value per member per day. And on day 0, the population consists of 4 members. There we go. And we want to find the population size after 5 days, and we'll do some rounding. So let's see if we can figure out how to frame this. So the question that we're being asked for is P of 5. So the population after 5 days. And let's see if we can, I need a little bit more room to work. Let me see if I can drag this over here. That's nice. Makes this a little small. All right, so we're looking at population, and so we've got an equation that must be, that's a little narrow. How do I change that? Can't. Can. A little better. P of t is going to equal our starting population times e to the kt. Maybe if I do this in opacity. Oh, that's much better. Could still do that in blue though. Okay, so we need to fill in some blanks in this sort of framework of this exponential equation. And let's go through the given information again. We've got a population that has a constant growth rate. So we have our K value. And we were told that on day 0, the population consists of 4 members. That would be this number right here. The population on day 0 is going to be 4. So let's just start plugging in some of this given information. P of t, actually it's, yeah, we can write this as P of t is equal to our starting population, which is 4, times e to the, and when they told us what k is, it's 0.8329 times t. We don't know what t is yet. So this is a nice kind of entry-level problem where we're just being handed some of the information. We didn't have to do a bunch of work with natural logs in order to calculate our k value. We didn't even have to plug in a 0 to a given formula for the population in order to find that the initial population was 4. That stuff was just given to us. That's nice. And then let's see, we've used our K value and our initial population of 4. Now all we have to do is find the population after 5 days. So P of 5 equals our starting population of 4 times e to the 0.8329 times 5. So these are my given problems. You can take this information and plug it into a calculator and get yourself a final answer. I will go ahead and tell you what that final answer is. It is 4 times e to the power 0.8329 times 5. Enter, and I got 257.44. We're supposed to be rounding our answer to the nearest whole number. So in my case, that's 257. And put a squiggly equal sign in there, approximately equal to 257. All right, so that is problem number 2. It's a nice little sort of warm-up / introduction to the homework processes that might be requested of us. The next one I want to look at is problem number 5. I assume this is supposed to say, a scientist can determine the age of ancient objects by a method called radiocarbon dating. And there's some backstory about carbon dating. C14, carbon 14, has a half-life of about 5,730 years. C14, half-life, there we go. Backstory. A parchment fragment was discovered that has about 74% as much carbon-14 radioactivity as does plant material on Earth today. And we want to try to estimate the age of the parchment paper. Okay. As I mentioned in the previous related video, there's a rhythm to these problems. So what we have is, we know that we're going to be using this exponential function, kind of a format, in order to solve this problem. And were we given a starting amount? We were not. Were we given a k value? We were not. So in this problem, we are going to have to figure out all of those things for ourselves. What we were given, however, was the half-life. And what that tells me is that, now remember that P of t is equal to P sub 0 times e to the kt. And we were told that P of 5,730 years is equal to P sub 0 times e to the k times 5,730. Here's what saves us. Because 5,730 years is the half-life, that means that, can I zoom out on this? Oh no. Really? I can't zoom out. Terrible. After 5,730 years, we will have half of the amount of carbon-14 that we started with. And the amount of carbon-14 that we started with is P sub 0. So I'm going to replace the left-hand side of this equation with 1/2 P sub 0 is equal to P sub 0 times e to the k times 5,730. So I finish with half as much as I started with after a very long time. What's the only unknown in this equation? K. So we have to solve for k. I'm going to divide both sides by P sub 0, which leaves me with 1/2 equaling e to the k times 5,730. Then I will take the natural log of both sides. The natural log and the e cancel each other out, leaving me with the right-hand side as just k times 5,730. Divide both sides by 5,730. And we've got our k value. Let me jump into the calculator and calculate a numerical value for that. So we've got natural log, I'm just going to type in 0.5. I'll close my parentheses, divided by 5,730 equals, and it's a small enough number that it gave it to me in scientific notation. And that would be negative 0.0001209689094, just in case you want all of that information. I don't ever want to have to type this number in ever again. So I'm going to hit my store button down here near the bottom left, STO arrow, and I'm going to store that in the variable k. So I'm going to hit alpha near the top left, and then I'm going to hit the letter K, which on my keyboard is above my left parenthesis. Enter, and it has stored it in my K value for me. Awesome. So now I'm going to rewrite my original equation. P of t is now equal to P sub 0 times e to the 0.00012, I'll stop there, times t. Let's see, what other information did they give us? A parchment fragment was discovered that had about 74% of the amount of carbon-14 as plants do currently. We want to estimate the age of the parchment. Now, I don't know about you. It doesn't maybe really seem intuitive to me what we're going to do next, but maybe it does. Maybe this matches up nicely for you. Originally, we were talking about half-life. So we kept the P sub 0 on the right-hand side of the equation, and we made the left-hand side of the equation say 1/2 P sub 0. There it is at the top of the screen. This time, we have 74% of the starting amount of carbon-14 remaining. So I'm going to change the left-hand side of the equation this time to say 0.74. In other words, 74% of the starting amount that was present is equal to the starting amount times e to the 0.00012 t. Divide both sides by P sub 0, and the only unknown that you got is t. So we'll have to solve for t in this equation. So let's divide both sides by P sub 0. Those cancel out. 0.74 is equal to e times this horrible k value times t. Take the natural log of both sides. If you want to put a little note over here that you're taking the natural log of both sides. Otherwise, I think you'll be able to tell because it says ln 0.74 equals natural log on the right-hand side cancels out the e, leaving us just with our gnarly k value times t, and then we want to divide both sides by that k value. I'm going to write divided by k. And that now says on the left-hand side natural log 0.74 divided by our terrible k value. I've really got it in for this k value. It's like offended me. Equals t. Now I can type in 0.0012 as my k value, but instead, in my calculator, I'm going to type in the natural log of 0.74, and then I'm going to close my parentheses, and I'm going to hit divided by, and then I'm going to hit the alpha button, and then I'll hit my k, which is above my left parenthesis, and now on my screen it actually says ln parenthesis 0.74 close parenthesis divided by k, and I hit enter, and I get 2,489.128. $2,489. I'm going to skip the decimals. Is my approximate t value. Now, this does say round your answer to the nearest year. Sometimes you run into problems like this and you always want to round up, because really after 2,489 years, I would not have gotten all the way down to 74%. It would still be 74.013% or something. So in order to make sure that you get all the way down to 74%, sometimes you have to round up to the next year. But here it just says round your answer to the nearest. Round your answer to the nearest 100 years. So we are, in this case, rounding up. We're actually going to round it up. If I were typing in my answer into WebAssign here, I would type in 2,500. What else did I want to say about that? Oh, does this answer sound reasonable? Because the problem takes so long and I've got this very large number and it's a time value, and I like to just make sure that it sounds reasonable. How can I decide if it sounds reasonable? The half-life, in other words, for half of the radioactive carbon to dissipate or degrade, would take 5,730 years. We only have to allow 26% of it to degrade, leaving us with 74%. So we don't have to take it all the way down to 50%. So compared to the 5,730, does 2,489 years sound reasonable? I would say that it does. If you had divided by the wrong number, if you had typed in divided by 0.0012, if you had left out one of those zeros, then your answer would be 1/10 as many years as it should be. You would have gotten 248.9 years. That is not a reasonable answer when you compare it to the half-life of 5,730. So don't hesitate to check in and make sure that your answers are sounding reasonable, whether it's a half-life or a population growth kind of a problem. Always good to compare your number to the numbers that were given to you. All right, I think I've had about enough of this section. I'll see you, where will I see you next? I'll see you in 3.9. Thanks so much.